Okay, so let's start. So yesterday we discussed the basics of computer architecture. What is computer architecture? Difference between computer architecture and organization, and something like that. So just go through that. So we are going the top-down approach. We discussed what is top-down approach. So looking in a system perspective, coming from the different systems within a application or different networking, different modules, top module, memory, what kind of memory. So coming from the top to the bottom level, right? The modules to circuits to devices to physics to the bottom, right? So these are things we will discuss in this course. First, we go to digital, computer architecture, processor control, memory, input, output, and overall working, and some advanced things like pipelining, right? So we discuss what is computer architecture. It is a science and art of designing, selecting, and interconnecting hardware components and designing the hardware software interface to create computing systems. That means functional performance and consumption cost and specific goals, right? The performance parameters in a chip is basically clock frequency, the power dissipation, and the area, right? So less area is better. And another important criteria is robustness, reliability, kind of. So this thing which we didn't discuss yesterday is like we are around surrounded by a lot of options, a lot of possibilities. Like that is something which confuses us, right? What is the confusion? We have a lot of options. Like we have uh, laptops with different configuration. We have 16 GB RAM, 8 GB RAM, even processors. We have i7 processor of 10th generation, i5 of 11th generation, and with some SSD hard disk. Some have, uh, you know, 512 GB SSD or versus 102 TB of HDD, you know, and SATA hard disk, and different lot of options. Different companies are offering different prices and and we have graphics processing unit in some cases, 2 GB. Um, you know, um, which the company? Yeah, Nvidia. Nvidia is one of the best companies offering graphics chips. That 2 GB, 4 GB, 6 GB, and the cost is also different configuration. Maybe you have 8 GB RAM and 4 GB graphics card, or versus 16 GB RAM and 2 GB graphics card, and with different kinds of processors, i5, i7, different generation. Same processor have different generation, have different performance, and we have different companies like AMD coming up with competition, very good competition to Intel. So a lot of confusion is there. What is better configuration for me? But ultimate answer is based on applications, but on your demands, but on your requirements and cost budget. You have to select the optimal for your specific problem or specific, some need for simulation, some need for gaming, some need for internet working, or root network analysis and all those things. So it depends upon application. And same is the case with smartphones. Smartphone comes with a lot of chips, a lot of processors, Snapdragon processors, and even Intel processors also used in this smartphones, and different RAM configuration, networking, and different even graphics units chips are also used in these smartphones because they need camera, a lot of cameras, 2, 3, 4 cameras, and all this has to be processed. And we need by default DSP processors in a smartphone. So all this is also part of computer architecture. So because smartphone itself is a computer, so there's also a lot of confusion. Which is the best configuration for me? A lot of options are available. So this course will also help us to understand what is the importance of memory, RAM, ROM, hard disk, which is the most important thing to consider. What are the options and why should I consider for my specific application? So although a lot of all the names, terminologies we are coming across every day when you are buying a laptop or smartphone. We have a lot of terms like turbo boosting technology and caches, different levels of caches, and graphics, different levels and generations of graphics and media, and different kinds of display, touch screen, right? And we have different number of cores, and some cores hyper-threading, some without hyper-threading, the multi-scaling, some are large, very large instruction word processors, right? Some are different cooling systems, are there oil cooling, water cooling, air cooling, and lot of things are coming on the latest processor. So it's very difficult to understand what is it. So this by understanding this course, we'll be able to understand what is the basics and able to understand what is the technology, what is we are right now, what are the difference, what are the different configuration technologies used in this laptops and processor configurations, and all of the pipelining and other. These are the old concepts, but You have to know how this is applied in today's scenario. And we should not get cheated also, because a lot of there are a lot of hype in the market that this is this. So we should know, is really benefit for the cost? It's another question. So, and the processor market is also very huge, and we have so many processor options. There are different kinds of 64-bit, 32-bit, and different quad core, hexa core. Even Intel is coming with 8 core. And the research purpose, we have 80 cores supercomputers, and some have multi-threading, hyper-threading kind of thing, without less number of cores with more hyper-threading. So we should know what is the difference between these two, and what is especially this also same with the case of DSP process also. So a lot of things we have to choose from. So a good knowledge of computer architecture will help you to select the best processor. Don't get cheated by any hype or unnecessary publicity things. And memory also the same. There are different kinds of memory cards, SD card, which is very familiar for us, memory stick, pen drive, flash memory, and we have other cards like SM card, SCF card, and X card. So if you understand one kind of memory like flash, magnetic RAM, ROM, SD RAM, DD-RAM, DDR-RAM, so we'll be able to DRAM and SRAM. So we'll be able to appreciate other kinds of memory and compare the speeds of existing memory. So the main thing is not, you may not learn all this highest technology memory in this course, but knowing the basic memory structures like SRAM, DRAM, and other flash and magnetic storage, SSD, will give you a better understanding of what is other options, right? Although we'll be discuss slightly about flash drives also. So then we may be able to compare the latest possibilities. Now this we had discussed yesterday, the Moore's law. There's a performance gap. The memory speed is not as high as processor speed. We are considering DRAM here. That is primary memory. That is other like SRAM consists of registers or high-speed memory, which is within the processor, like caches and other things. That is very costly and takes a lot of area also. So we won't consider that as a primary memory. So we put the DRAM. So DRAM speed is much less compared to processor speed. So this is the bottleneck. Okay, all the Moore's law is allowing us to reduce the size of transistor, but the memory processor disparity, the change in difference in the speed, and processor is still huge. Okay, so this is a slight example of what the speed analogy. So this is, you can see aircraft, you can see an ant. So aircraft is going very high speed, 900 kilometer, 1000 kilometer per hour. So but ant is going at speed of few centimeters per second. Even 1 centimeter per second may be I'm looking at the maximum. In the case. So how an ant will going to interface with the aeroplane? For example, ant is on ground, aeroplane will be take off on the sky. So if ant want to talk something, or to deliver something, or transform data or some piece of goods to the aeroplane, is it practical? It is not practical. Why? Because the speed difference. There's a lot of disparity in the speed. You can see it's 250 meter per second aeroplane, but speed of the ant is 0.01 meter per second. So difference is 25,000 difference, 25,000 in the magnitude. So this is not practical. So how will you expect an ant to communicate or transfer some goods to the aeroplane? So that is the challenge we are facing in the semiconductor or in the computer architecture. So bottleneck between memory. So ant represents your memory, and the airplane represents the. But this analogy is not perfect. This is much. The difference is not much compared to real. So the better analogy will be the between the ant. Sorry, not ant. Snail and a high-performance Boeing jet. Now the snail is 0.1 millimeter per second. Its speed is very less. So when you compare, the difference is around, you can say this is 25 lakh, right? 2.5 million times the difference faster. This aeroplane is faster than the snail. But in real life case, this is much better than the memory, hard disk, or magnetic memory versus the current process speed. So the difference is like this. It is more than 25 lakh. It is 200 lakhs. That means 20 million times faster. Memory processor is 20 million times faster than your hard disk operation. Hard disk is operation of milliseconds. Hard disk usually operate in milliseconds. That means hundreds of operations per second. That means 10 milliseconds. That is hundreds of operations per 1 second. That means 100 operations in 1 by 1000th of second. So that means can say 1 second is I'm just considering as 1,000 milliseconds. So 100 by 1,000. That means 1 by 10. Right. So it takes 10 milliseconds around. It is actually a faster version, I'm saying. But here in 1 second, only 100 operations are done in a magnetic storage. So why I'm comparing magnetic storage? Yeah, magnetic storage is smaller, slowest memory, especially where your operating system and other things are loaded. Even when you see a film, you can don't expect all the film, maybe 4 GB or 2 GB films are put in your RAM. That's my primary memory. Most of the film data is also video or audio, whatever, it is put in the hard disk only. So it is like a kind of kind of technique, a trick uh, which make us feel that the processor is working at very high speed along with the memory. But memory is actually slow. But we are doing some different tricks, hits and tricks, to make us don't feel that the memory is so slow. So there are a lot of tricks. We call virtual memory. We had different paging. A lot of get affected by the slowness of the memory. Although we have different hierarchical memory, we'll discuss that. We have registers, temporary storing, and we have caches, we have RAM, primary memory, and this is secondary. So I'm just comparing magnetic memory versus latest processor, which is working on 2 gigahertz, 2 into 10 raised to 9 operations, and 100 operations. So which is much slower than snail also. So this is we had discussed yesterday. More slow. We again discussed yesterday. And what is architecture? What is organization? What is the difference? We also discussed. And abstraction also we discussed. We'll be discussing top down, coming from the application networking and all those things to OS, micro architecture, and logic and circuits. So we'll be discussing in the yellow part mainly, and basic understanding of logic and basic circuits are prerequisite for this course. So there are a lot of applications in all especially in automotive, consumer electronics, medical, automation, etc. So this we have discussed all those things, and we have to decide how much RAM I need, how much processor capacity, GPU is required or not, what is the input output speed, USB 3.0 or USB 2.0, what is the difference, what is DMA, okay, so what are the techniques I can use to speed up my process. So programming also we discuss high level and low level programming. The high level is we don't care about the hardware, but low level assembly language we will be using instruction set given by the specific processor company or the specific hardware features given to us. That is assembly code. We will be discussing about assembly code in this course. Now we have different kinds of architectures right now. We have different kinds of processors in the market. So our project or application may be dealing with heterogeneous processors. Maybe one may be a quad-core processor, and there may be a DSP processor, and there may be FPGA. So different processors and their accelerators which help to speed up the application. Right. So we have general purpose computers, processors, hybrid memories, and all those. Okay, so why should we study the computer architecture? So we should understand both hardware and software, because we have to utilize the advantages of both without overusing it. We cannot waste much area, because if you are using a general purpose CPU, you may be losing lots of area, and we may be not as fast as what we want in our application, and our power consumption may be huge. So, and software level also we have to optimize whatever is required. We don't need a full-fledged, for example, for a simple application, for example, for a gadget, we don't want to load the whole operating system like Linux or Windows. It is too, it's too heavy. So we need a simple operating system, or a simple, if it is real-time, we need real-time operating system, RTOS, RTOS. So likewise, we need a simple thing so that it doesn't consume our processor operations. We just need very light processor based on application, light OS or whatever software based on applications. And it is also important, understanding of architecture is important for problem solving, troubleshooting, and other improvements and R&D. So right now is a very important time because processors are very cheap. So knowledge of computer architecture can help you to design a lot of systems, and with less cost, with less consumption, lower power consumption, maximum frequency, and especially these days, the three walls, this is given here, three walls: energy, reliability, complexity, security, and scalability. So security is also becoming very important these days. And what is scalability? Scalability is, say you have a your dedicated core doing your application. So can I increase without doing much changes in the software and hardware of already existing? Can I increase the number of processing? Maybe I can add 4 more cores to make it 8 cores. So is it scalable? That means I can increase the load, or you can increase the processing capability by adding more chips or more something extra. So scalable and reliability is also important. Security is also important, right? So at the same time, you should reduce the complexity. So this is something, and big data is another keyword these days, because a lot of data is generated by a lot of, we have a lot of cameras. Cameras has become cheap, like processors have become cheap already. Cameras also becoming cheap, and sensors, like all this becoming, IoT devices are coming, and IoE, internet of everything is coming. So all these are generating a lot of data, and these data are stored also, and we need to process this data. So we need a lot of, a lot of processors, a lot of computing systems to analyze them. So this was a past system. We had a single microprocessor, which is general purpose, and we had a main memory, and we had a hard disk or storage, magnetic storage. This was a past system where all those things were simple. We don't have much application. We needed a word processor. We just need networking and some simple operation. But right now the things are very complex. There are different kinds of processors you can see. FPGAs are the general purpose, quad core, hexa core, all those different cores you can see within a process, and they have different kinds of memory also. We have flash memory, SSD cards, and other general purpose memory. DRAM is also used. We have a lot of SRAM options also, right? And last option is the permanent storage, and networking is also another important part, which is not shown here. Cloud storage is also cloud. We can put our data on the cloud, right? That is on some servers available. We can use the servers for processing also. We can reverse GPUs, CPUs, like Google Colab is a good example. We have Google is providing us a Python, means a lot of languages it can run. It will give us free GPUs and DPUs for our work, etc. So that's also another example of cloud computing. So this we have discussed functional basic of a basic operations or functions of computer storage and processing. So we need a control mechanisms to regulate this data movement. So this is the functional view of a computer. Okay, this also we discuss peripherals and communication lines. Storage and processing is what we expect we need to connect a lot of peripheral sensors. And so this is your display, memory, input, whose data you're using is ALU and control it. So this is different things we'll discuss in the course. Processor we'll discuss, and again control unit, how is the control design, what is control unit, what are the duties, and how we design all the types of control units, etc. This is a basic control flow. We have a lot of instructions which we can write in assembly language, or we can write a high-level language also, like Python, C, CPP, or Java, MATLAB. It can just convert into instruction codes by compilers and interpreters kind of thing. Then they'll convert your assembly code into machine code using assemblers, right? And this will be going to the instruction interpreter in the control unit, and the control unit understand what does this instruction means, right? What is the meaning of the adding means I have to take data from which registers, from which memory, right, etc., etc. So the data is taken and is registered. So all things are decided or controlled by the control unit. So we'll discuss all those things. So these are different parts of the control unit: instruction register, and this instruction is stored in this register, is processed in the control unit, and the control unit output is control signals, which tells which all the units registers should be allowing data to flow, which all registers should be closed, which all processing, addition, multiplication, division, what is to be activated, and where the result is going, etc. So all those decided by the control signals, right? So the control bus carries the control signals. So the overall idea is given here. We'll go deeper as we discuss things. And memory is another important part. We'll discuss what are different types of memory. Caches are the main memory, RAM, right? SRAM, DRAM, and we have DMA. We need to write or read faster. We need DMA. And networking also, memory is also used. And we have hard disk, magnetic memory. So all this will be also discussed. So this is something which A lot of research is going on this to improve the reduce the performance gap, to make the memory faster, make the processing not affected by the slow memory. So you can say like this. So then input output will be discussing multiple different input output devices and how they interface with the high speed CPU. Input output units are very slow because humans are using keyboard. Keyboard typing is very slow. It is happening few keys per second. Or a mouse is scrolling, the movement is very, few millimeter per second kind of thing. So this is very slow compared to processor speed. So processor should wait for the input output device. No, we should not wait for the input output device. So how to synchronize this thing? That's a problem in the IO unit. So this is this typical speed. So you can see it is very slow. It's very slow. You can see in internet, when it comes to internet working or in connection to internet, this is very high speed. You can see it going gigahertz. You can see this is gigahertz. This is the internet 10^9 speed. And other things like keyboard and mouse, you can see only 10 bits per second. Mouse is also slow. Modem is also slow. Floppy disk, lesser printer, right? And display may be faster because we have high definition HDD displays, etc. And networking may be faster. So this is a functional view. There are address lines, data lines, and control lines, which is connected to input output unit. And these input output unit will be interfacing with the processor or memory using this address, data, and control lines. So this synchronizes the data transfer between the input output and the processor or the computer. So this is a typical look inside inside a processor. You can see different units like floating point unit. So this is the blue thing. All this, I think the blue means the memory, cache memory. And inside, yeah, there are different units. You can. It's not visible, but this look of the view. What the hardware structures inside a typical processor. We have floating point unit, pipeline control unit, integer unit, integer register files, multimedia unit, clock unit, caches, data translation buffers, hardware page form. So a lot of things which is related streams. So this is basic things which we expect in a processor. FPU stands for floating point unit, and TLB means translation look inside buffer, caches, integer units, instruction fetch and decode is part of control unit, and bus controller, IA control. So this is a typical processor, Intel Itanium. Its name is Must Core. So this is a typical view. So this slide is basically telling you how much power dissipation, right? So this is a typical chip after calculating how much power dissipation the chip is taking. You can see the small units is shown interconnect RAM, DRAM, read-write memory, 60 nanojoules. Nanojoules is used for that thing. Read-write, DRAM, read-write nanojoules. All those nanojoules is quite significant power dissipation. Whereas you can see this 64-bit data point at 20 picojoules is the energy consumed in that thing. Picojoules. You can see compared 16 nanojoules and 20 picojoules, right? So, and we have interconnect. What is interconnect? Well, I think there is a buses. It can be 256-bit buses. It's also in the taking 1 nanojoule. It's also significant power. So you can see the main thing here is the processing. The processing is becoming less power consuming, but the interconnect, the data transfer and communication is becoming more and more expensive, power expensive. So this is what happening. So how to reduce the power dissipation in data transfer? That is another challenge. And one of the main reasons of this is we can say the length, wire length. Wire length is as the technology is reducing, or transistor size is reducing, the conductor size, which is maybe copper or even sometimes silver or aluminum, whatever, is also the size of the conductor or the wire conductor is also reducing. So as it reduces, we can see the area to conduct is so resistance. As the area reduces, resistance is increasing. right? And length is also increasing as our chip size is reducing. We have a lot of features, core, different cores, a lot of cores within one chip, one chip. So what happens? The length of the conductor is also increasing. A is decreasing, L is increasing. So resistance of the conductor is increasing. And resistance of conductor is increasing. I square R loss is also increasing. I square loss is increasing. They also cause some delay, right? RC delay. And so there's some capacitance. We have a tau or delay, time constant. Delay is R into C. So resistance increases, delay also increases, and the capacitance also increases. Then delay significantly increases. So there are a lot of problems happening when we scale the chip to a lower technology or advanced technology from 12 nanometer to 7 nanometer, our resistance is increasing. So a lot of power consumption is delays causing problems. So one solution is we can reduce our voltage VDD or VCC. So, but that's also we don't have much swing. What is swing? Our VDD is this 0.9 volt to 0.7 volt, which is actually very difficult to work with because we don't have much noise margin kind of. Because when noise comes, our one becomes zero, zero becomes one, and a lot of challenges. So this is the main catch. So memory access consumes 1000x energy of a complex addition. So this is comparing this. This is 25 core joules consumption, and 16 nanojoules consumption is of a read write memory access. So 16 nanojoules compared with 26 or 20 picojoules, so around 1000 times difference. So this is the one of the challenge which is the research community is working on how to reduce the power consumption, how to increase the speed of memory access, how to reduce the memory processor disparity, etc. Right? That much of this from yesterday's. So maybe any quick doubts or any points I can take. I'll just try to uh, discuss that point. As we'll go to the second. Today, the main problem was the point of discussion is digital logic review. So we'll try to review. So digital logic. Okay, so basically, digital we just although you have learned, so we just brush up what are Boolean theorems. B into one equal to B. That is a property of AND gate. So when one is there, it is allowing AND gate to pass whatever data coming in the other input. It allows to pass. So B into one equal to B, right? And B into zero, and gate is off. When we one for the dual, changing the the changing the sign, and in the sign the B becomes B bar. Okay, dual just changing the sign, and it becomes or it becomes and, like that. So one becomes zero, zero becomes one. Okay, so dual is also right. You can make a dual of any Boolean expression, and we can say that is also a tautology, or that is also a true expression. So that's it. So we have some more Boolean expression you can go through just for brushing up. So one of the important things is these things are we all discussed already. You know already. It's not difficult. And De Morgan theorems also. I think last line is Royce De Morgan. So B0 into B1 dot B2 etc. All bar. Split the bar, change the sign. Split the bar, and you can change and into or into and. And minimization, you know how to minimize a complex expression. We take the common terms and reduce using Boolean loss, and we can reduce the complexity. I think this again, the last thing again can be reduced. B bar can be taken out, and then we C bar plus AC. That is A plus C bar. I think we can again reduce. I think so. Okay. Yes. Okay, you can go through De Morgan's theorem. So A and B can be converted into A bar, no A bar, or B bar. right? So this is De Morgan's laws of NAND. Nor also we have De Morgan. A nor B can be converted to A bar and B bar. We can just switching. Yes, what we are trying to do, we're trying to change the bar. The bar here is converted given to both A and B. That's it. So spirit now A got the bar, B got the bar, but when the bar is taken from the or nor, it changes to and. That's it. Similar things happening here. This bar is splitted. Yeah, this bar is fitted to the both A and B. So that A bar, B bar, and splinter to OR. And splinter to OR. That's it. Now start with multiplexer and demultiplexer. So before that, we should know OR and NOR gates are sensitive. I'm just telling you OR and NOR gates sensitive to what? Sensitive to 1. And AND gates are sensitive to what? Sensitive to 0. Why I'm saying this? Because suppose I have a AND gate, right? Suppose an AND gate, I give an input, say 1. Now when I give an input 1, I don't know what is my output. I don't know what is my output still now. But if I have similar AND gate, if I give input 0, right now I'm very well know that the output is surely a 0 or a 0. So I can say same is the case of NAND gate also. Whenever there is an input 0 to the NAND gate, I'm sure that output is going to be 1. So you can say even if input of an AND gate is 0, or sorry, input of an AND gate is 0 or input of an AND gate is 0, the other input is becoming don't care kind of thing. Don't care. I don't care what the other input is. I already know my output. That means NAND gate and AND gate are very much sensitive to 0. Because AND gate input is 0, output is definitely 0. I don't care about what the other input, right? So that is one case. So similar to the case of NOR gate. NOR gate, if one input or gate, sorry, OR gate is 1, and that output is going to be 1. I don't care what is the other input is. Can it be A, B, X, Y, whatever. So it is more sensitive to 1. And same in the case of NOR gate. If one input is high, I'm very well sure the output is going to be 0 in case of NOR gate. So I don't care about the other input. So I say this is more sensitive to 1 in case of OR gate and NOR gate. And AND gate and AND gate are more sensitive to 0. That's it. Just simple things. Okay, now what is multiplexer? For multiplexer, main application of multiplexer kind of best example is telephone switching. We have a lot of people calling to some locations through a single channel. Channels are limited. We have limited channels from India to USA. Even optical fiber cable, you should know the limited bandwidth. So a lot of people will be trying same time. A lot of data transfers happening. So we have to multiplex them, right? We have to multiplex them. All the people has to communicate through single channel. So multiplexing means there are multiple inputs. We have to select a few of them or one of them, and we'll allow the transfer first, and then we'll allow the transfer second, so on and so forth. And demultiplexer is opposite. We have one channel or one input coming. We need to spread them, share them into multiple outputs. So that's it. So best example is telephone switching for multiplexer and demultiplexer. Right. So this is so multiplexer. You should know we have multiple inputs and single output. So we have to select. We need select line. If you have n inputs, how much select lines you need? Log n to the base 2. For example, you have four inputs to the multiplexer. How many select lines you need? Log 4 to the base 2. That is 2. If you have 64 inputs, how many select lines you need? Log 64 to the base 2. That is, I can say 6. Right. So 6 select lines are there. Likewise, we have 1024 inputs. How many select lines you need? 102 log 1024 to the base 2. That's 10 select lines. Right. So this is which we are know. So what is typical application? Whenever you think of multiplex, you should think that you have some song which is stored in your MP3 player, laptop, satellite TV things, or in any of places where you have some songs stored, your pen drive, flash memory, whatever. Now, among the different options, you have to select only one option at a time because you only one output, surround system, one speaker, one output. So you have to select one of these devices, song stored in one of the devices using some select switches. If 00, your MP3 song from the MP3 player is played, and so forth. 01 is will be from laptop, 10 should be satellite TV, and 11 is the cable TV. Whatever. So this is a selector, multiplexer is selected from multiple inputs to a single destination. Now this is circuit which we know that the same concept, AND gate. AND gate is sensitive to 0, and whenever one input of AND gate is 0, the AND gate is off or turned off. So this is the principle I'm using multiplexer also. Using select lines, I'm going to switch on and off the AND gates. Because A and B will be have values, so that one of 0, 1, 2, 3, one among the 4 AND gates will be on. All the AND gates will be given one input is 0. Okay, so that is why I'll be switching only one AND gate on based on A and B, and so corresponding D data D0, D1, D2 is going to the output Y. So this is the waveform. You can see the waveform, input data, select line, output data, etc. You can see it. Now there are different chips which if you're done lab, you can see the different type of chips, 16:1 marks, 8:1 chips, 8:1 marks, etc. available in the market based on application. Now we'll see what is demux. We know demux is only one input and it has to be shared among different outputs. So it has to be channeled to one among n outputs. So this is similar. We have one input, and if there are 4 outputs, how many select line? Again, we need log 4 to the base 2. That is 2 select lines to channel the single input to the corresponding output. So this is also a typical example of demux where you have some file stored in your system, a single file stored in the system. This has to be, maybe it has to be printed through laser printer, fax machine. It has to send through fax or inkjet printer. So we have a lot of options, plotter printer, etc. And you need to select one file in the system and let it print or scan or network or send through network, etc. So this we need to select the output device. So multiple output device or single input device. So we need a demux here. And A and B selects which destination your file is going to go. This is a typical switch. Here also the application is simple. And different 4 AND gates. How many outputs? We have 4 outputs. So how many AND gates you need? 4 AND gates. So who will switch on of the AND gates? The A, B selects select signals. A and B will let X go to any one of those outputs. So only one of the AND gates will be on based on the A and B, and that AND gate will conduct your X. X can be 0 or 1, sure, but that will go to the either D0, D1, D2, D3, right, based on A and B. So this is your typical demux. So this is a waveform, typical waveform, and we can just compare the input is X based on select 1, 0, S0, S1. You can say the X is going to D0 initially because S1, S0, and S1 is, you can see here, X is high here. So based on S0 is 0, S1 is also 0. So the D0 will be getting the value of X. X will be going to D0 initially. And after some time, we can say S0 becomes 1. Now the X is still high, and now that is going to D1. X is going to D1. Now we can see select lines, and now S1 is going to high right now, and S0 is going to 0. Now we can see D2 is going to get the value of X. Now X is 0 here. That's why you can see X is 0 here. That is why D2 is also getting 0. Again, you can there is a change. S0 is going to 1. And S1 is also going to 1. So 1, 1. So now the value of X is going to the D3. Likewise, again, this value S is changing 0, 0. So again, X is getting 1, X is getting 1, and D0, and so on and so forth. So different chips configuration for demux also. So now encoder. What is encoder? Something which codes. There is some input, and I want the input to coded in a special sequence or special language. Is encoder. Which codes the input. So input is say a decimal number, output will be a coded sequence or coded value of the input decimal number, right? So maybe here we can say ABC. So we have different, how many inputs are there? There are 8 inputs, 0 to 7, D0 to D7, 8 inputs. So among this, any input is on, my output ABC will be coded version of that input. If the input is 0, if I press the D0 switch, if I press the D0 switch, output A will be 0, B will be 0, C also. So this is the code for the 0. For corresponding 0, my encoded communication is 0, 0, 0. Now if it is 1, D1, you can see the D1 is going through the C. C is becoming 1. So C is becoming 1. The rest of the things will be 0. So this is corresponding to 1. Now what about 2? 2, we can say 2 is going to this value B. So 1, 0. So this is going to be 2 version of. So this is the coding till 7. What about 7? Gets, can say 7 is connected to all this 3 gates. So this is 1, 1, 1. So this is the coded version of 7. So this is encoder. Whatever the input, this value is getting coded into a binary or any system. Encode. So decoder. So here also you can see decoder also the AND gate principle is used. AND gate, we have 4 AND gates in the output, and based on that onning and offing or the sensitivity of those AND gates, my output is becoming 1 or 0. So based on the value of A0 and A1 here, we know there's how many possibilities of A0 and A1. We have possibility 0, 0, 0, 1, 1, 0, and 1, 1. Right. So based on those, either D0, 0, 0 input is 0, 0, the output is going to be D0 is going to be 1 high. If it is 0, 1, D1 is going to be high. If that is 1, 0, D2, 1, 1, D3 is going to be. So this is kind of a decoder. Based on this, if 0, 0, I'll get 1 will be higher, 2, also you can say 0, 0, 1, 2, 3. So this is the output. So this is input is a code. We have some kind of binary code or some kind of code as input. This is my input. My output is the decoded version. So 0, 0 stands for 0, 0, 1 stands for 1, 1, 0 stands for 2, and 1, 1 stands for 3. So this is the decoded version. We have solved the coding, and this is decoder. So this is decoder. This is only 2 to 4 decoder. You can have any number of size of decoder based on application. Now adder we know that adder needs a XOR gate and an AND gate and OR gate also here. So we have some binary expression for full adder. And what is full adder? We have 3 inputs, 3 single binary inputs going to the circuit, and we have only 2 outputs. One is sum, one is carry out. One is sum and one is carry. So this is a single module of full 3-bit adder, and this is put into this full adder circuit, and we can have 4-bit, we can have 8-bit, 16, 32, etc. So, but here the initial CZ may not be used in case of a 4-bit adder. Can be given input 0. Okay, so we can have a so combinational sequential. Okay, so this is just different types of combinational sequential logics. Combinational. What is the difference between combinational sequential? That you already have discussed. Like combinational logic is whatever the input. Right now, dynamically, my output is going to change based on my input variation. There's no memory, there's no storage, right? There's no dependency on previous input or output in case of combinational. They're just whatever the input at right now, instantaneously, the output is going to change based on the logical conditions, right? That is combination. There's no storage, right? And what about sequential? There is always some storage. Previous value, previous input or output is going to affect my present condition. It has some memory. Sequential logic has memory, combination doesn't have any memory. It can immediately take decisions. So sequential logic take decisions. So, and combinational logic can say already we discussed the input dynamically acts on the gates inside the combinational logics, which is without having a storage or previous dependency. It's giving me the output in real time, instantaneously. But sequential logic, we have some memory like flip-flops. Basically, we might have stored some previous values of output or input, and it is going to affect in my output, present output. Right. This is about the sequential logic. Now, flip-flops. Flip-flops. Difference between flip-flops and latches. Flip-flops are edge triggered. We have positive edge and negative edge of the clock, and flip-flops are designed such a way that there are a lot of issues of level triggering. multiple switching. You can have multiple switching within one clock. So we don't be able to control the outputs. How many times the output is going to switch in kind of level triggering or latches. Flip-flops are that probably limited because it's positive to negative, positive to low going edge, or negative or low to high going edge. Different kinds of flip-flop: D-latch, D-latch, SR, JK. So okay, this is an example of RS flip-flop. So there are two output complementary, Q bar and Q. So there is okay, you can go through it. So we have to set and reset and Q bar output, and based on the gate is NOR or NAND. We have different kinds of options. In NOR gate, it is 1 is invalid, whereas in NAND gate 0 is invalid. NAND gate 1 is not changed, whereas in NOR gate 0 is not changed. This thing just this is basics to have some idea. Hello.
Yes, sir.
My slides are not changing. Okay, fine. So I'm just sharing the slide and go through it. So next tomorrow we'll discuss the synchronous and asynchronous circuits, and we'll go to the maybe number system also we'll discuss. I think let's stop it here. You can put your roll number. If any Q questions I can take, you can just ask them in Q questions.